All right, Red Nation. Today we're going to be talking about pre-process, especially in X-ray radiography, going from the X-ray acquisition to making an image which actually looks like an X-ray image. Coming up here at How Radiology Works. The first step is actually the physics of the interaction. We've talked about that before in our videos about CR and about DR, so I'm not going to go through that here. But we're actually going to talk about analog to digital, and we're going to talk about other pre-process, including quantization. First off, the analog to digital step. In the case of DR imaging, you have your X-rays that are coming in. They're going to interact in the detector like we've talked about. An electrical signal is going to get generated. It's going to get stored in a little capacitor right by the detector element. Then that's going to get brought down to what's called a multiplex, which is going to say essentially take turns for the signals to get processed and read through an analog to digital converter. So this is also called an A to D converter. Or the CR, it's also a digital modality, but the digitization happens inside of the CR reader itself. There's a latent image we've talked about in our CR video. That latent image is on the panel, and that is going to get read out by a laser. The laser is shining and in a raster manner scanning over the panel. And as it scans over the panel, light is going to come out. That light is going to be read out by a photomultiple tube, converted to electron, amplified those electrons, and further amplification here till finally that analog signal gets converted at an analog to digital converter, or an ADC. As part of that conversion, there's a step where you need to make the measurement, and making the measurement, you have an analog signal, and then you use a process to measure that analog signal. In the process of measuring that analog signal, the precision has to do with how many gradations you have. So if the analog signal is how big is your foot, and we measure that, we're going to look at a ruler, write a number down, and that's going to be a number that we can convert essentially to a digital number. So we've gone from an analog distance of how long is your foot to that digital number. And based on the ruler and how many tick marks we have on the ruler, that determines the precision of our measurement. We talk about this as being the quantization effect. So there's specific levels, and the fact that we have specific levels is quantization of our signal. Imagine the X-rays come through the patient. They're interacting at the detector plane, and if I draw a line of what the analog signal should be at the detector plane, imagine the analog signal should look like this. And this is just kind of a made-up signal, but this is a function of the distance here on this axis, and then here is the actual signal. So we can get an idea of a couple factors here, both the effect of the spatial sampling and then the effect of the sampling of the signal or the quantization of the signal. In terms of quantization, if we don't have very good spatial sampling, that means our actual detector elements are going to be kind of wide down here. And if we don't have very good quantization, that means we actually aren't going to have very many individual levels that the signal can be read out at. The bit depth of the system actually determines how many individual levels we have available when we're doing this quantization. If we improve just the resolution alone, you can see now the bins are actually smaller. But if we don't have a high bit depth, namely we only have a few different levels that the signal can be measured in, then we're still not able to represent our signal very well. It's still going to be very blocky in that respect. So we need a high enough bit depth, and if we have a high enough bit depth, the bit depth is typically 2 to the n levels. So where n is the number of bits that we're using to discretize the signal, we get 2 to the n different levels that we get to choose from when we're actually doing that measurement. Now you can see we can actually relatively well represent the signal here because we have a fine enough resolution to do the measurement, and we also have enough bit depth. So we have less quantization error when we have this higher bit depth. Then if you were to look at an image and that image was just actually air alone or a nice flat piece of metal that we're imaging, and we expect to see a nice flat response, what you're actually going to get is something that looks like this, where there's different blocks on the image, and there's different what we call bad pixels. The bad detector elements are defective detector elements. There can be individually bad detector elements, and then there can be lines of bad detector elements. What is done is there's a process to identify those bad detector elements, and then we replace the bad detector elements with an average of the neighbor value. That's what's called interpolation. So we can go from the raw image to an image that looks like this after that bad pixel correction. Then we still have an image that looks like this. So because there's what we call different gain and offset of the electronics during that quantization process, even if you have a nice uniform signal, it's not necessarily all uniform here on the image. So we need to do what we call a flat field correction, where we take measurements at that uniform signal, and then we normalize so that after the flat field correction, we can get a nice uniform image. So the bad pixel correction, the flat field correction are really important to do in order we have an image that looks like an actual image. Additionally, the histogram is an important feature space that we can look in. An image is a two-dimensional matrix, and we're storing all the values within that matrix. And in the histogram space, now we're condensing that information down to just one plot. And what we get here on this plot is for each intensity level in the image, we say how many pixels in that image actually have that value. What you can see is that the human body actually doesn't have that many different types of tissue here. And you can see there's a little bit in the bone space. There's a lot in the soft tissue space. There's some in the lungs as well, because there's a good amount of lung field here. And then there's a little bit of air down here. And the histogram can get used by users or by processing algorithms to actually look at the exposure and to determine if the exposure was done relatively well, was really washed out in one way or another, the histogram would actually be skewed. Now you know all about the pre-processing, but do you know about the CR and the DR physics of how the actual X-rays are going to interact? CR videos on CR and DR next, coming up.